So we'd like to now look at the last section we're going to cover in this class. This is it, right? So if you are at this point, you have learned everything except for this section in college algebra. So here we are. This is on exponential models. So we'd like to apply and understand how do we use exponential functions to model real-world situations. If you remember, way back in the beginning of this chapter, we had talked about how useful this is to describe things that grow exponentially or decay exponentially. So we'll see a whole bunch of examples, understand how do we do it, what are some scenarios in which this makes a lot of sense. But in all of these, we're going to model exponential growth and decay using this function. A of t is equal to a sub 0 e to the kt. So this is our general exponential growth model. This was similar to p times e to the rt, but I'm just going to use these other letters just so we can differentiate between these. So what each of these represent, a of t, this is going to be the amount after time t. Now, whatever the amount is, maybe it'll be some type of chemical product, maybe it'll be some type of population. It'll be the amount. In time t is going to be dependent on the situation. It could be in minutes, it could be in hours, it could be in days. As long as t is clear from the context, we're going to be using that as our time. A sub 0, this is going to be our the initial amount. So this number that goes in front, that is the initial amount present. So that'll be often pulled from context, figure out what that initial amount is. T is going to be whatever our time is, whatever units, whatever amount of time we have, and K is going to be some rate per unit of time. And often it won't be given. So K is going to be one of those that we're going to figure out what is the rate that things are going to be increasing or decreasing. What is the rate that things are exponentially growing or exponentially decaying? So we won't know what that is. We're going to use something from the problem to help us solve for K, and that'll be what we're looking for. But a few things to note about K, though, is that if K is going to be greater than 0, so if K is positive, this rate is positive, what that means is that we have exponential growth. So this is going to be exponential growth. On the other hand, if K is going to be less than 0, so if K is something negative, we're going to have our exponential decay. So this is just something small for you to check, that in situations where things should be getting smaller, your K, if you evaluate that, that will be something negative. If it should be growing, then that K is going to be something positive. So this is our general equation, and so we'll do a bunch of examples to be able to understand how do we use this and how do we now apply this to very meaningful models. In my opinion, these are going to be some of the best, most useful, interesting models we're going to study in this class. A lot of things that are exponential use this as opposed to something that's linear. It's a little bit harder to really always be linear. So we will take a look and understand how we use this.